So good morning, everyone. So today we have a presentation this morning on MAQAO, developed by the University of Versailles by my two colleagues, Emmanuel and Jasper. And this afternoon you will have a presentation of the Forge tool suite. So I guess we can start. So Emmanuel and Jasper, you can start now. Okay, the slides are already uploaded on the Collaborate if you want.
Okay, but I can't see the slides.
If you choose share, if you share content and share files.
Okay, I can share the. I have three options. I have empty blackboard. I have screen.
I have screen.
Oh, there is
there is a sound loop.
There is a sound loop.
So maybe someone has loudspeakers and should use a headset.
Never mind. Never mind. It stopped. So you can see in share content.
Okay, so I can see empty blackboard. I can see window. I can see webcam, or I can see a file, a PDF file.
Yeah. Click on file, share files. Yeah. Jasper already launched it.
Okay, I have MAQAO Zone.
And MAQAO is already being shared. So.
Okay, perfect.
MAQAO is being shared. Yeah. You can.
So I can. Perfect. So. Hello everyone, I am Emmanuel from University of Versailles. With my colleague Salah, I will present you MAQAO, a performance analysis and optimization tool. So to get maximum performance of an application, it is important to extract performance at every level during design steps, starting from algorithm up to execution. For instance, even if you have a good implementation, but if you are using bubble sort to handle a large array, you will have much lower performance compared to a quite bad implementation, but using a smarter algorithm to sort, for instance, a merge sort. So all steps are really important, and performance tools and methodologies have some job to help you at the different steps. So some questions should be followed. So that is some methodology. First question is how much of an application can be optimized, and most important, maybe should be optimized. If some part requires, for instance, weeks or months of optimization, maybe you have not the time for this. So we need to really to focus on things that are profitable to do. Second step, if you want to optimize something, you need to measure. You need to measure performance of the code. That is locate where some loops or some functions are spending most of the time, most of the application time. If you are optimizing some code region that is costing only 1 or 2% of total total time, you will just lose your time. Third step is to understand why so much time is spent. So clearly you need tool to do this. And you need to understand in which step, in which layer you need to work. This algorithm, implementation, or compilation, etc. And the last step is now you understand why some loop or some function is quite expensive. An important step is to understand how to optimize it. If we know that it is expensive, but we can do nothing, the job is finished. So clearly, optimizing a code is a multifaceted problem, starting with pinpointing hot regions, typically loops and functions, and to identify at which level, generally at implementation level, but could be at algorithm level or execution level. For instance, an issue with load balancing and threads will be available on the core, etc. After that, you need to generally optimizing is just exploiting at best your hardware. To sum up, it's just parallelization. So it's using different levels of parallelism that are multiple nodes with MPI, multiple threads with OpenMP, SIMD, single instruction, multiple data instructions with vectorization, etc. But memory is also important. Memory hierarchy that are memory data caches, cache level 2, cache level 3, etc., and DRAM. After that, you need to take attention to the global speedup and not only the local speedup. Having found some loop, I don't know, which takes 20% of execution time with some speedup, some good speedup, adjust for this loop locally is not sufficient to be worth the case to optimize. So typically, optimizing 30% of application time can provide a lower global speedup, so can be less interesting than optimizing only half, 20%, if local speedup in the 30% region is not strong enough. So that is explained in this slide, where you can see with you have some lower speedup even with 40% total time compared to the second case, covering only 20%, but having a better local speedup. What is important is the product of these two figures, 20% multiplied by 50%, for instance. Now let's start with a motivating example. So this is a typical loop from Polaris MD, molecular dynamics application, in which we can see several issues. First one is this loop is not small. You have many statements. I will try to use some. Can you see the mouse now? Maybe to pinpoint some. I will try to use this. Okay, so first issue is high number of statements. It is more difficult for the compiler to optimize this. This is the first issue. Second issue is very slow memory data accesses, non-unit stride and indirect. So indirect, you are using another array to know the actual index in your array. And unit stride, that is, for instance, if you have an array T, instead of doing Ti plus 1, Ti plus 2, etc., you will do, for instance, Ti plus 100, Ti plus 200, etc. It is much less efficient for a processor to deal with this. Next problem is divide square roots. These instructions are much slower compared to additions and multiplies. So maybe we could try to lower the cost of this by replacing divide by multiplication or hoisting, for instance, the divide out of the loop. Next issue, the fifth one is reductions that needs to execute an iteration of the loop before starting the next iteration. In other words, we're introducing dependencies between iterations that is reducing performance. And the next issue here is the number of iterations of the loop. In other words, the loop trip count is not known at compile time. That is, you are preventing your compiler to apply some optimizations. For instance, if the compiler could know that the iteration count is always 4, it could apply some smart optimization. For instance, remove this loop and replace it with its body duplicated 4 times. Some questions? No. Okay, so now let's try to answer to all these issues, to this optimization challenge with MAQAO, so which means Modular Assembly Quality Analyzer and Optimizer. So a first keyword is modular. That is, we have a core, we have a kernel, an API on which we can have some modules, some tools that will interact each other and benefit from a global view presented by the code, global structure of your code. Next term is assembly. So MAQAO is working at assembly at binary level that will have some advantages that we'll describe in next slides. Quality analyzer, that is, you will have not only some performance performance profiles, that is 20% spent in this function, etc. But you will have some analysis about this, to have metrics and to have reports in plain English. For example, there is this issue, you can fix it with that, with compiler flags, etc. And the next term is optimizer, that will help you to not only measure performance, but to improve it. So clearly, MAQAO targets HPC codes, HPC applications, mostly at core level. It is able to deal with parallel codes, but focus will be put on core level performance. MAQAO will not optimize for you your code, but it will guide you to optimize it. It will help you to do so. About some characteristics, it supports Intel x86-64, Xeon Phi. It is open source, LGPL3, developed at UVSQ since now more than 15 years, and is very easy to install since you don't need to install it. It's just SCP of a static executable. Okay, so MAQAO was used on various real-world HPC applications in various fields, for instance, CFD, computational chemistry, or molecular dynamics. So molecular dynamics, we have Polaris, presented before with the example loop. About CFD, we have help optimization of YELS2 and AVBP, and quantum chemistry was for the application QMC equals chem. For some of them, we got speed up to 3x on some data sets by different strategies. For instance, hoisting some functions repeatedly called with same input parameters, typically exponentials, out of critical loops. That was done, for instance, for QMC chem. So MAQAO was funded by UVSQ, so University of Versailles in France, but also by Intel and CEA, the French Department of Energy. So an association, which is Exascale Computing Research, which is a lab, and French projects and European projects. MAQAO is used by different tools like TAO that was presented Tuesday, and for instance Intel Advisor that is bundled with VTune, etc. to typically analyze vectorization. A former MAQAO member team also created an ISV which is called the Pexel that contributes also to MAQAO. Okay, so here is a quite exhaustive list of people that are contributing or have contributed to MAQAO. So many are PhD or was PhD students or postdoc, but we have some other situations too. Okay, so as I previously told, with MAQAO, choice is to analyze at binary, at assembly level. That has many advantages. Normally in grid part presented Tuesday in the introduction talk. So to sum up, at binary level, what you see, what you analyze, is what is actually run by the processor. So you have no distance between between the compiler and execution. So MAQAO will directly analyze and instrument what is actually executed by the processor. That is binary code. Compiler optimizations are then fully taken into account and preserved after instrumentation. So that is a big advantage compared to source instrumentation. So to do so, MAQAO reconstructs the program structure, typically as functions and loops, and relate it back to the source code to help you optimize loops and functions. For instance, about loops, let's dig into loop unrolling. With loop unrolling, the compiler will split the original source level loop in several binary level loops, typically the main loop to handle iterations 4x4 or 8x8, and another loop which is called epilogue or tail loop to handle leftover iterations. So, okay, in the source code, you will see only one loop, do I equals, etc. But in reality, in the processor world, you have not only one loop, but you have at least two loops, one unrolled loop and one another loop that will deal with leftover iterations. And MAQAO is aware of this. So basically, main structure of MAQAO consists in disassembling and then analyzing your application, so as binary files, .so, .executable, etc. And we'll expose this as an internal representation. So basically loops and functions, but not only this. With a Lua interface, so it looks like a subset of Python, so it's quite similar to Python, so it's script. And different MAQAO tools like LProf, CQA, and OneView will use this internal representation to generate some results that will be aggregated by the OneView meta tool to generate HTML but context reports. So the methodology used by MAQAO is clearly loop-centric. So most of analysis will be operated at loop level on loops to locate two types of bottlenecks. CPU bottlenecks, so CPU bound bottlenecks, and memory bound bottlenecks. For CPU bound issues, we will mostly use the CQA tool, code quality analysis. But we can use also more advanced tools like differential analysis and value profiling. Typically, value profiling consists in extracting the number of loop iterations, so the dynamic trip count and cycles per iteration metric. And for memory bottlenecks, we can also use some differential analysis, which consists in removing some instructions in the loop and comparing performance before and after, so with and without instructions, and compare. If we have no difference, that means the removed instructions has no impact, no significant impact, etc. So it's a really pragmatical approach. And we have some other tools to do some characterization of memory behavior. So the first question about performance is where time is spent. So this is a role of profiling. So in MAQAO, the profiler is called LProf for lightweight profiler. Lightweight means we will use sampling and not instrumentation. So that was explained Tuesday. So advantages and drawbacks of these two approaches. So here we are using sampling. Big advantage, many advantages are this is non-intrusive, no need to recompile. So we are directly operating on the binary code. Overhead is quite low, let's say 2%, and can be adjusted. So by tuning the sampling rate, you can adjust in the same time the overhead. Granularity is typically loops and functions, but we can have other granularity levels with LProf. For instance, the whole module, or only parts of loops, which are basic blocks. Now we can know which loops are interesting in terms of cost, execution time. We need to analyze them. That will be done with CQA, code quality analyzer, that will analyze the quality of the code generated by the compiler, and will work completely statically. That means no execution of your code is required. So as soon as you already know which part of your code is interesting, you can just run CQA on specifying identifier of the hot loop or the hot function. It has some nice features. For instance, possibility to cross-analyze. That is, what if as well, for instance, instead of Sandy Bridge, what if Skylake, etc. So you can analyze for a target which is not the host target. So the target, the processor, which is actually running CQA. That allows some exploration for performance. So is it interesting or not to upgrade, for instance, cluster nodes? So it is loop-centric, mostly targeting compute-bound issues, opposed to memory-bound that will be deal with other tools. And to be very easy, three parts. First, what is the problem in plain English? Second part, how much you can gain if you fix this. And third part, what you can do with your compiler and your source code to get this estimated speedup. So that is basically what CQA is doing for you. Main concepts of CQA is based on the fact that in real-world HPC applications, only 5 to 10% of peak performance is used. The goal of CQA is to reduce this gap, is to help you. It will not do this for you, but it will help you to reduce this gap and to improve, for instance, sustained actual efficiency from 5 to 10 up to, for instance, 20 or 30%, or maybe more. So to do this, CQA will compare the peak performance in the target processor with your actual performance based on the region of code, the input region of code as generated by the compiler. That means analyzing, that means for CQA, analyzing the pipeline, so how different instructions or micro instructions will flow together in the pipeline, and analysis usage of resources, most of resources being execution units. For example, to deal with floating point addition, floating point multiplications, loads, stores, so loads memory reads, store memory writes, etc. So key levers that are explored by CQA, so not all of them. It has some other tracks, but just on these slides we can see vectorization. So that is using SIMD instructions. You have some figure here. So for the same cost, instead of computing only one element in a vector, you will compute 4 or 8 elements for the same cost. That means 4x speedup or 8x speedup. So this is done by the compiler automatically if your code is not too complex. So MAQAO can help you with this. Second point is avoiding expensive instructions, typically divide and square roots, by replacing them by multiply, etc., if it is possible. Second, third step that will be explored in a later slide consists in guiding your compiler, helping him to provide, to generate a better code with a better quality and better fitted to your target processor. And the last point is very important, is about typically data arrays and reshaping, reorganization of arrays, especially if they are 2D or 3D. There are some ways for the processors that are much more efficient compared to others. Typically, you need to focus on regular accesses, stride 1, unit stride. So to use consecutive elements. This is very important. Okay, so CQA can help on two aspects: compiler and source code. About compiler is your friend, hopefully your best friend in optimization challenge. That needs, with a friend, you need to talk to him and you need to listen to him. CQA will help you in for these boss tasks, especially to better understand what is doing. So first aspect is to force your compiler to exploit instructions that are supported by your processor. By default, your compiler limits to instructions available in first 64 bits x86 compiler. Now, processors, that means 20 years ago, 15 to 20 years ago. So the first Athlon 64 bits. So in other words, you need to explicitly specify to your compiler a target processor to fully exploit your processor capabilities. CQA can guide you with this task and will automatically detect what is the compiler you has used, which options was used, which is your target processor, and he knows you, so you don't need to learn this. He knows which magic flag you need to use for this. For instance, with Intel compilers, if you want to optimize for an AVX machine, for Sandy Bridge or Ivy Bridge, like Archer, you need to compile with -x host on an Archer compute node. Second point for compiler is about to force some optimizations. So for some reasons, it will not apply some optimization. Maybe it's more complex, it's too complex, or it's too conservative. And you can talk to your compiler via compiler flags or compiler directives. That is some special comment lines just before your loop to force your compiler to, for instance, vectorize or unroll some loops. So it's the same than the previous item. CQA already knows for you which directive to use according to each compiler vendor, etc. And third aspect is to bypass some by default, the goal for a compiler is to provide semantically correct execution. That is not, and that can be opposed to best performance. So it is conservative, but it's up to you to bypass this behavior. Now, the second part is about source code that needs for you from you some code transformations. There are two tracks for this. First is improving data access, typically by loop interchange. And second aspect is avoiding, that is in generally replacing with other instructions, so high latency instructions like divide square roots. So typically for divide, you can multiply by the reciprocal. So if the denominator is constant across all iterations, you can, after the loop, just before the loop, pre-compute the reciprocal of the denominator. And after that, in the loop body, instead of dividing by this denominator, you will multiply by the reciprocal. And the multiplication is less expensive, is much less expensive compared to divide. Typically 5 or 10x factor. So now about one view. So I presented it before as an aggregator from the results generated by the different tools, typically the profiler, LProf, and the analyzer, CQA. So reports are generally available by default in HTML format, so you can directly open them in your favorite web browser. But also some other formats can be supported, like XLSX, so Excel, or text. So if you are on compute nodes in a console, that can be in a terminal. That is quite convenient, quite often to adjust some fast text output. So main steps of one view consist in first pinpointing hot loops and hot functions using LProf, and after that, on these hotspots, apply CQA to help you, so to understand what is happening, how much you can gain, and how you can gain. So available results is basically what I had just told, and also can provide some speed up predictions. So by taking into account the local speed up and the global coverage, and by product of the two terms, can provide some actual application level speed up that is that can be related to some return on investment. So you can, for instance, know that okay, you can have a 20% speed up, but that will be very difficult to obtain. For instance, that means that will need from you to optimize 100 loops. So in that case, it will be difficult. In other case, you will have, for instance, only 8% speed up, but to recover this, to get this, you only need to optimize one loop. In that case, it's really interesting to proceed. Also, OneView can monitor parallel applications, so OpenMP, MPI, or both, and can monitor so typically the cost for all threads, and help you to diagnose, for instance, a load imbalance. Okay, so I have finished for this part, and I will leave the talk to Salah.
Hello, everyone. I guess if you all can hear me. So my name is Salah or Jasper. You can choose any one of them to refer to me, and I'm going to be taking charge of the next part. So what you should do right now maybe is pull out a terminal and then start playing around with BT, because it's a tool that has already been presented. So you should be familiar with how to compile it. But I'm going to do a live demonstration of running these commands and then the output, so we can explore a little bit more actually what MAQAO provides as metrics and analyses. So you should have access to the slides, so technically you should go and download them, and then you can go in and open a session on Archer. And I'll share my screen right now so I can show you the steps. Yeah, this one. Here we go. So let me know if you can see my screen, if it's visible, if you can see clearly actually. Okay. Is this large enough? Cool, great, good. So now you have a directory in the work. If you go to the oh, I'm back. I don't know. There was a little issue with my internet connection. I guess there was a disconnect. So can everyone see my screen?
I can see.
Okay, good. Yeah, there was a slight disconnect for a moment. Yeah, I couldn't see my my screen actually on the Collab app. So if everything is all right, let's keep going. Okay. All right. So as I was saying, you have actually here in the /work TA002 shared, you have a MAQAO directory. So try to copy that into your work directory, and then you should have actually these two applications available. If you go here into this directory, once you copy it, you should go in it, and you'll find actually the examples directory. In there, you should have, I mean, the NPB, the NAS benchmarks. You can copy them from the shared tutorial directory, and then Lulash is provided. So you can untar any of those two or both of them. And we're going to try to run MAQAO on both and look at the output. So once you extract, we're going to start with the NAS benchmarks. So I already did a run to test. And what we're going to do here is make BTMZ. And this is going to be a BTMZ class C, and then nprox late. So I suppose that you already switched from the Cray to the GNU GCC environment. You should follow the same steps as was shown actually on the BTMZ presentation on how to compile and run it. And once this is done, you should find here, oh, I made a mistake. I wanted to compile the C, but, oh, slash should be in capital letters.
So this demo is based on slides that are available in the website.
Oh yeah, you can go and fetch the files in the shared file. So technically, I'm gonna move from switching. I'm gonna share the slides in here. So, oops. So you should be able actually to follow these instructions in order to run MAQAO on the hands-on exercises. And also you can go in and follow the slides in here. Okay, so you can go in and run these two commands, but I'm gonna switch back to sharing my screen and I'll show you a live demonstration. Okay, so once you compile the benchmark, so it compiled the W, which I don't really need. I'm gonna remove this one. So I already did a MAQAO run. Okay, so what you should do now is go and copy the BT MAQAO PBS and the config file for the one view module. So this one is the batch file for the batch manager for the Arch cluster, and this one is the MAQAO configuration file that allows one view to run this binary and profile it using the two MAQAO modules that Emmanuel presented earlier, LProf and CQA. So what we should do here is just go in and run the command that you have on the slide, MAQAO OneView, and then -- create report equal to 1, and then we're gonna give it a config file, and this should be the config file. You should find these files actually in the MAQAO hands-on archive. So I'll show you actually where to find them. So let me go back here, and you should go into the MAQAO hands-on directory, and here if you go into the BT directory, you should find these files. So the BT MAQAO PBS, the batch file, and the Lua configurations file. So you have one for interactive mode in case you work in on a node actually interactively, and this one is in case you use actually a batch manager. So we can look at these files if you want, and we can go through the configuration details. And well, one thing also, maybe if you didn't do that, and maybe I forgot. Yeah, I forgot about this. I'm sorry. You have to go actually and source the load MAQAO.sh. If you want to load MAQAO into your environment, you have to source it so that you don't have to specify the MAQAO binary path every time, so that it gets integrated into your environment. And it's a simple script that just adds the yeah, as I said, actually you have to follow the same steps for compiling BT as you did before. So you have to switch from the CRAE environment. You have the procedure to switch from the CRAE environment to the GNU environment. And don't forget to source the load MAQAO.sh. And technically, if you type in MAQAO, you should have a this. So you make sure that it runs, or you maybe type in help. But eventually it should be added to your environment. So once you go into the MAQAO hands-on, you have BT directory where you have the PBS and the config files for OneView, and you also have another one for Lulash, which is another application we're going to run MAQAO on. So once you copy these files, go back to examples, NAS benchmarks, and go into the bin directory, and here we have the binary file. This is the binary file in question. Yes. So let's look at the BT, the config file, the MAQAO config file, OneView, and this is going to be the PBS-based version. So this is Lua. It's, as Emmanuel said, a programming language that's a bit close to Python. And this is a script that contains actually markers and symbols for the OneView module to be able to run your application on a cluster using actually a cluster configuration. So maybe I should switch this into Python mode so I can get some colors. So what you have in here is the name of the binary file. So in our case, it's btmz _ c-8. And then here, there's marker actually used by OneView so that it doesn't have, you don't have to specify the name every time. This is sort of like a variable you can use anywhere in the program. And this is a Lua script that's used as a configuration file actually for the MAQAO module. Here you specify actually the batch script that you want to use to run your application. And if we look at the bash script, then okay, this was BT, I'm mistaken, _ MAQAO.pbs. And here you have everything set up so you can load your binary into a node and run it. So this file is going to be actually loaded by the MAQAO script and used to by OneView to run your application. So what you have in here is the details of how you run an application using OneView and how you configure the run of the application. So the number of OpenMP processes. You can set up these according to what you wish, depending on the application you're running. You can deactivate MPI or activate MPI. You can put all the binary parameters. We're going to look at some other binaries maybe with parameters later. In the hands-on session, we might dig deep into using MAQAO with different applications. And if you have your own application, it would be interesting to see actually what we can do. So this is just an example of the files in there. If you have any questions, feel free to ask. I mean, we're here to answer any questions you have about the whole environment. And what we're going to do now is I'm going to try to run OneView, and we're going to create report 1. So OneView has many levels. There are many report levels. So the one we're going to use right now is OneView 1. It's first level that invokes CQA and LProf. So the both modules that Emmanuel talked about earlier, lightweight profiling and static analysis. And they'll be aggregated into HTML reports that I'm going to pop up once the run is done. And here we're going to specify the config file. So everything we need to run this binary file with all the parameters and the inputs and everything that has been set into the config file is going to be used to execute this application and run MAQAO on top of it. So the config file is going to be the config, and this one is PBS. And I guess that's it. That's all we have to specify. We can start the run. Now, once it's done, we should have a directory with some profiling data in it, and I'll show you how to copy it back. You should definitely copy it back into your laptop or your local unit and use a local browser to open actually the HTML report, because I don't know if the -X or -Y works with the SSH. I'm pretty sure it doesn't. And if it does, it'll be probably slow to run Firefox actually from a distance. So you might as well just copy the files locally and then explore the content and the reports actually locally. So now apparently it's done. So it's going to format the results. Yeah, we have 81 loops total. So the report is being generated. Now it's going through the functions. We have 41 functions apparently in this program. Cool. So it should be done any second now. Yeah, it's good. So this is the new directory with the new BTMZ run. So what I'm going to do is copy it on my local machine. This is so this is my home machine, and I'm going to copy this. Maybe it's going to take some time to copy all the files locally. So in the meantime, you could maybe look at the data that I just pulled out before. So what I'm going to do now is I'll show you actually some outputs. It's the same one as the one here, what I'm pulling right now is I did a couple of runs prior to this demo, so we can already look at some already recorded data. So maybe the 08. If you want to visualize the data, just use a Firefox or Chrome, and you should go into the directory /results, capital letters. So here you have two directories. So I did a run at 8:26 this morning, and the run that I just did right now. So we can go to this directory, and you'll find actually all the raw data in there. So this is the report, and you should have an index.html. So what I'm going to do here is on my local machine is just open the index.html. Now remove this and let me bring that Firefox window. So this is what a OneView report 1 looks like. What you have in here is the total runtime. So it took around 22 seconds to complete a whole BTO run. And here you have actually tabs, so you can see more information about the application. So clearly here we have 96% of the time spent in binary, then we have MPI and OpenMP. And then we have the functions tab where you can look at profiles. But then let me share this. If we look at the loops profile, this becomes very interesting because we can clearly see here the coverage per loop. It's nice to look at functions, but usually if you look inside a function, what you'll find is either a loop or a bunch of loops. So usually in HPC, most workloads are in loops, are processed in loops. So here we can see the zsolve function that takes around 764% of the time, and it's loop number 207. If you want to see, and it's an innermost loop, so you can also see the classification of loops actually on the last column. So if you double click on the loop, MAQAO will go in and fetch the source code if it is available. If it is not available, what you'll have is the assembly code instead. So you can look at the assembly code of your function. So here clearly we can see that this function isn't really. Let me zoom in a bit. The code of this function is a mix of SD and PD instructions. So we can see some vector instructions mixed up with some scalar instructions here. And we want to go back and look at the assembly code, source code. So this is the zsolve.f function. And on the right, you have actually a CQA report that's shown with an analysis that tells us that only 26% of vector register length is used. So we have partial vectorization in here. And then if we totally vectorize the loop, we can gain a 2x speed up, which means that this program still needs some optimization or some compiler guidance. So if you want to look at more details, you can see here that store and arithmetical instructions only vectorize loop at full power. Here you can see actually that tool proposes a bunch of compiler flags to add. Maybe recompile with F associative math, include an OFAST, and maybe remove inter-iteration dependencies. So it's providing you with a bunch of propositions that you can maybe apply next time you want to run this binary or recompile the binary. So here they're much detailed. You can have the hints tab, where you can see that the tool detected a constant unit stride actually in here, and then it proposes a bunch of workarounds to try to reorganize and consider permute loops in case these optimizations are helpful in depending on the code in itself. Here there is a type of elements and instruction set that were detected. So there is 195 SAC or AVX instructions, 70 addition or subtraction operations, and 125 multiplies. So this is a quantitative quality evaluation actually of the code plus vectorization. But if you look at another loop, for example, like xsolve, now this one has almost the same profile. So we have the same speed up. So these two functions there have absolutely kind of like the same assembly code. If you want to see some detailed pipeline simulation or port evaluation, port consumption, throughput evaluation, you can look at the expert view, where you can see actually for each port of the target architecture actually the state of each instruction, or the state of each instruction for each port. So this is a more of like an expert view for those who want to dig deep into the assembly code, but in general, you can just go through. So this is a lab. We're going to look at some more intricate applications for which we can find some pretty interesting things. BT is just an example of an application you can run to test the tool and see actually overall what MAQAO provides you as an output. So this is the basic view on which you can find actually a bunch of pretty helpful information, like the potential speed up that you could gain if there were a number of loops, 80% of, if most of the loops were optimized, what could you gain actually from your optimizations? And a quantitative value, I mean, you gain like a 2x speed up, or you gain like maybe a 1x or 1.01, 1.05. So we won't gain much from these optimizations, but if we do vectorize, we have around a 40% speed up, which is not bad. So the tool here also says that the f-enroll loops is missing. So maybe this is a flag that we should try and well, support for automatic vectorization usually is at compiler level. So your compiler is already going to try to automatically vectorize the code if you provide the proper flags. Like if you go with an O3 or an OFAST and try to push vectorization on the compiler, it might do auto vectorization. Now, what MAQAO does, it will evaluate the quality of your code by first running a static analysis tool like CQA, like what you saw in here. If you go into this second loop here, and you can look at the report, we're going to run this on another binary file, and we might have some pretty more interesting information. So what CQA will do is go through your code, or the bunch of loops and functions that you have in your code, and try to evaluate how well is the code vectorized for the target architecture. So you can clearly see here like that we're only using 26% of the vector length. So we're definitely not using actually the total capacity and possibilities actually that the machine provides. And that we still have like a 2x speed up to gain if we do the job properly. So this usually lies on the compiler's shoulders. This is why Emmanuel said that the compiler, you should treat it as your best friend. You should try to figure out a way to make it do the things that you want it to do, like vectorization, for example. So the support for auto vectorization is usually at compiler level, and compiler, actually, the developers are trying to do their best. It's just that there are some languages and some code patterns that are very hard to vectorize, especially with C. C has almost no notion of memory or memory array. So it's only pointers going everywhere. So the compiler has a hard time tracking actually which is a vectorizable and which is not, because of memory overlapping and alignment issues and so on and so forth. And what CQA does for you is just evaluate, for example, the vectorization efficiency, as Emmanuel said in the chat. And that is done through an analysis of the assembly code, of a data dependency graph, and so on. Yeah, well, Fortran code is usually easier to vectorize than C code, because it has kind of like the language is designed with the idea of an array, like a memory spot that is bound. But in C, you only have pointers, so it's pretty hard actually to vectorize code and to have vectorized code. But there are ways you can work around this, as Emmanuel said. If you follow usually the CQA advice, you will reach much better vectorization and a better relationship with the compiler, let's just say, that will allow for vectorization and other optimizations to unfold. Because usually this process of optimizing a binary is pretty tedious, because sometimes you stumble upon a code pattern that not only just stops vectorization, but many other optimizations from happening in the compilation pipeline. So the best thing to do is try to resolve the easiest ones first, so that you can open up the doors for better optimization. So sometimes if the compiler manages to vectorize, this opens maybe the door to easier enroll and much better throughput and much better bandwidth in a kernel code or somewhere where you require actually vectorization and performance. Yeah, you can use actually compiler reports, like with ICC, you can use the opt report to generate an optimization report where you can easily have information about where the compiler failed to vectorize. And the thing is, sometimes, as Emmanuel said previously, there is a problem with the software development process in general, that what you run is not what you have written in text. So you write a C code or Fortran code, but then you have to compile it. And what the compiler produces does not necessarily reflect the way you think about it on the machine as it does in reality. So the programmer is very distant actually from the end product, which is the binary file sometimes. So this is why we try to focus on binary analysis, because as it was said before, you analyze what you run. And tools like CQA manage to, for example, catch these small loops that the compiler couldn't vectorize, for example, and that might hinder some other additional optimizations in the future, or might just break performance at some point just because there is some code pattern, or maybe the language is not the proper one. But the compilers are getting better and better. And the performance analysis tools are also getting better, because we have more experience now with all these code patterns, and we have dabbled enough to be able to separate the good from the bad and to do some little pattern matching and to develop algorithms around all of this. And CQA is just a product of all of that. It just goes through your code and analyzes the assembly instructions and tries to figure out whether you code is efficient given a certain computer architecture. So this is what you'll probably see if you go through the expert output and try to see each and every assembly instruction and its state actually in the whole pipeline. But MAQAO is not going to vectorize.
Can I ask a quick question? Sorry, I've not been able to attend all this session. Apologies, but I've seen issues where the compiler appears to generate vectorized code, but it's generated multiple versions of a function, and it panics at run to do with memory alignment, for example. And so although the binary has lots of vector instructions in it, at runtime it panics and runs the non-vector version. Can you pick that up? Sorry, that was a problem I've seen in the past. You know, your binary has lots of vector instructions at the assembly level, but there's a switch and it doesn't run them at runtime. Is that something which you've come across?
It does happen sometimes, because what binaries now do, or what compilers do, is CPU dispatching. So they're gonna insert a CPU ID somewhere at the init of the binary file. So when your program is running, it's gonna detect on which architecture it's running, and if it does have a version that is suitable for that architecture, it will run that version instead of some general purpose compiler.
The issue I saw actually was that it had generated it was a vector architecture, but it generated multiple versions of the function depending on whether the memory, the arrays were aligned or not aligned. And so at runtime, if your arrays weren't aligned, although the hardware had vector instructions, it didn't issue them because it picked the non-aligned of the routine. And so kind of a simple, naive sort of grep of the binary for vector instructions gave you the wrong, gave us, you know, was misleading, is what I'm trying to say.
Yeah. So
this is an issue that could be, yeah, go on.
Yeah, go ahead, Cedric, go ahead.
I was just saying that this kind of issue could be identified with MAQAO, because the profiler will see the loops that are actually being executed. And by analyzing this one, we'll be able to see that the assembly instructions inside are not vectorized.
Yeah. Okay. Fine. Yeah.
Yeah, but the thing is, I think I got what you were talking about. I mean, will MAQAO be able to say that the version of this function that's been executed is the vectorized version or not?
Yeah. Yes. Yeah.
Yeah. Well,
yeah.
You can do that with CQA if you know the function itself. You can run a CQA analysis. I mean, if we come in here, for example, let's just say that it's the compute RHS here, and you go through the CQA, you will see whether it was the vectorized version or not. But you will have to provide MAQAO with the function. It will not detect automatically whether it is the vector version or not. But it will tell you if
exactly what you said, that the code that is executed is often very different from the code you write, because the compiler does, clever things.
There's so many transformations actually on the code that, in general, actually, if you don't know the architecture, you will have a hard time actually understanding what's going on. So, and the closest thing to the architecture is the assembly code, so you don't really have much choice at some point. You have to go down to the binary level.
And again, apologies, I may have missed this at the start, but do you support the ARM processors?
We do have support for ARM, but it's not really that extensive. We had an engineer work on it for a year. We do have static analysis on ARM and a little bit of profiling, but we haven't really pushed it that far because the engineer who was working on it actually left somewhere else for a better future, let's just say. But we do have support, and it's ongoing. Actually, we didn't drop it. We plan on picking it up later on, but we need actually access to ARM machines to be able to run, because the development was done mostly on a simulator and on a I guess a Cortex A57, a machine that was designed for embedded systems, not for HPC. So we're in
a collaboration with ARM. We have an ARM64 machine with quite a few nodes, I don't know, 20, 30 nodes in it.
So it's a KVM. Is it a KVM or a Marvell, a Thunder X2, something like that?
It's Thunder X2.
Yeah. Well, I guess we had access to a Thunder X, not an X2, when there was when we were working on the support for ARM. But it's actually ongoing development. Just didn't.
There's also well, it's not more. There's a Cray, there's a large Cray machine in the UK, which has ARM. It's effectively Archer, but with ARM processors in it as sort of a again, that's a genuine bespoke HPC machine, but with ARM processors in it. So that's something you might, if you're interested, I don't know, I just thought it's just that with the ARM processors, they're going for very big vectors. So vectorization is absolutely essential to get performance on them.
Yeah, they have the new SVE instruction set that just changes a lot of things actually, especially for compiler vectorization. They have made it.
You can dynamically select the vector length. Is that how it works? I can't remember how.
You can select the vector length, so you can use the size of the vector that is adequate for the computation that you try to do. So you don't have to get stuck only with single precision with 2 elements per vector or something like that. The vector length is dynamic. So and we have actually I think we did have support for SVE, as I said. The engineer that was working on it was working on a simulator, the SVE simulator provided by ARM. But I don't think we went really far actually into the instrumentation. I mean, I don't think there is support for it yet. but there is lightweight profiling and there is a CQA. So we can actually build I think a 1-view-1 report on ARM, but this will require like a little bit of development for some time. But we never really went really deep into it because we're mostly Intel funded, and most supercomputers and CPU, HPC, CPU users actually use Intel, or AMD.
Yes, or AMD,
So,
yeah, but yeah.
But by the time ARM comes into the market, I think MAQAO will be ready for it. It's just a matter of if it's widespread and well used and well documented. Yeah, sure. I mean, it's just a matter of putting the effort into it, so we can just put some support. But we started doing it like a while ago, but just the lack of machines, the lack of access to the HPC ARM environment, that kind of like slowed down the development process. But sure, if we can have access to machines, yeah, sure, we can push it. I don't think it would be an issue. So to go back here to the presentation, we can also run actually. Now we run this actually on the BT benchmark. We can run it on another application that's also normally provided with the examples in the examples directory. It's called Lulash. It's a code that does computer simulation that's provided by the Lawrence Livermore National Lab, if I'm not mistaken. And the interesting thing is this code uses MPI. So, and it's very easy to compile. All you have to do is, because it's already compiled, I have to clean. All you have to do is a make. And it will use MPI here. You can see that the MPI flag is set to 1. And it will use also OpenMP. So the interesting thing is you can see MAQAO run on an OpenMP MPI, a hybrid HPC application. And this is a small pro application that simulates some HPC workload. And it's a pretty good benchmark actually for analysis tools. And it's written in C++. So we have another layer of complexity. Is C++ code is very different than C code. And let's look, or Fortran. So what we're going to do here is exactly the same as before. You have 2 files that are available in the hands-on /lulash directory. You have the config MAQAO Lulash, which is the Lua file for configuring the 1-view run, and a PBS file for running a job actually on the Archer cluster. So same as before, we're going to go with the 1-view create report 1. MAQAO 1-view -- create report 1, and the config file this time is going to be the config MAQAO lulash.lua. And if we just run it, it's going to be the same scenario as before, and we should have actually same report as before. So this is just a demo example. I already have so I downloaded actually the other file. Maybe we'll look at it. But I already have a run for Lulash that I did before. It's this one. So I'm going to go open a Firefox and go in here, results, and then Lulash. And then here we have an index.html. So if you open this one up and I bring that window right in here. There we go. So this is the same report as before, but on a different application. So this time, this application took like around 25 seconds to run. And we spent 80% of the time in loops, mostly innermost loops. We can clearly see that we have almost 80% of the time spent in loops. Time in user code, 85%. There is no unroll loops used with the binary flags. And we can clearly see here that the array efficiency is 63%. So this code is not really that good. There is still room for improvement. We can do better. And Here we have all the details about the architecture and the environment. So the moment where we started the run, the experiment type, it's an MPI experiment because we compiled and rewrote it with MPI activated. Details about the CPU, the Linux environment, and compiler flags, and so on. And here we have actually the configuration summary. So we can clearly see actually the content of the configuration file we used. If we look in here, same as before, we have a pie chart where we can see how much time was spent in binary code and outside. And technically here, when you have external libraries and so on, they will be flagged actually with the proper colors. Maybe we'll look at this in more details actually when we go switch into the hands-on session. Same, we can look at some function profiles. As I said, usually it's a loop inside a function, unless the function is called within a loop. It's rarely actually a function that's a hotspot. So here we're looking at the source code of the lulash.cc of the function in question, the loop inside a function in question. And we have a pretty interesting CQA analysis. So 13% of SAC AVX instruction are used. So we can gain a 3.15x speed up if we do vectorize this code properly. So CQA here proposes to use another compiler, to use different flags as it did before. Maybe use a struct of array instead of an array of struct if that is the case because of memory alignment issues. If you use actually an array of structure, you will have a lot of address computation code generated by the compiler to deal with the offsets and the different fields inside of a struct. So usually CQA provides a pretty interesting analysis in here about the load. 1% of the loads is vectorized. There are not load, store, addition, subtraction. Okay, so we do have a lot of vector instruction used, but they're mostly not memory instructions. Okay, we can look at the assembly code if we want to. So obviously, yeah, we have partial vectorization in here. Obviously, we use HPD, so high and low vector. High and low vector chunks. It uses unaligned UPD, which means the unaligned memory instruction. So this is pretty bad code, and it generates XMM code. So it generates actually SAC code instead of AVX, knowing that we're running on a machine that does have AVX. So it's an Ivy bridge, so it should have AVX too. So this is a just broad view of the output. We can look also at the, I guess here I run it with a single thread. So maybe we should do a one with multiple threads.
We may have reached the pause soon.
Okay. So like
it's 10:30, so maybe we'll take a break now and resume at 11.
Sure. Do you want to start again at 11? Okay.
Yeah, sure. I mean that's unless we're going for a few more minutes, but maybe it's better if we stick to the schedule.
Okay, so this is Emmanuel. We will resume MAQAO hands-on with two other applications, two other benchmarks. So I'll try to share my screen. Okay, MAQAO hands-on. So first BT, Lulesh, and we will deal with the third. Can everyone hear me?
Yes.
It's okay? Okay.
Yeah.
Okay, so what I think is a good deal. You can open for in half of your screen. You can open slides that are available in the collaborate. No, in the website. And for the other half of the screen, you could use the collaborate to see my terminal. That way, you will have both slides and the end zone and my end zone terminal. Okay, so for the moment, we are on slide 18. So I present a very naive matrix multiply kernel consisting in in a three level loop nest. So it's very typical, classical. So I don't need to explain more. And we will see that with by default, performance is not so good as we could expect, even if with reasonable compilation environment, that is a reasonable flags and a version of the compiler which is quite recent. Okay, so it's slide 19. So I will share now my my terminal. Okay. So we will use for this end zone an interactive session that is more convenient. So you can just so we need to log in as usual. As usual, we need to log in to Archer. So slide 2. So we need.
Can you please increase the font size a bit? It's a bit difficult
I will try.
to read.
And now it's better.
Yeah, maybe a bit more. Yeah, that seems good.
Do you prefer a black or a white background? So for instance, something like if I try with a this, it's better with a white background or not?
Oh, okay. Oh, nice
Okay.
tip.
Okay, so now I will increase size.
Size is okay now.
Okay. Alors, go back. So now we are on Archer. So for me, I need to reload the MAQAO environment. Okay. So I go back to slide 19. So first, I will open an interactive with -i session with one node. 20 minutes should be sufficient for this. I use a reservation for today. I will lose all my environment. So it's a choice. You can use a V with a Q sub to export the environment, or you can start with a clean, empty environment. And in that case, you need to again source the MAQAO environment, and we will use the GNU compiler instead of the CRE compiler. So I export the work environment variable since it is more convenient. So now I can, for instance, use cd $work. So now I am on slide 20. So we will go into the matmul directory, matmul and zone directory. So you can play in parallel if you want. So if you want to try, you can just enter commands as I'm doing so. And I will compile the first naive version with make. That was already done just to be to play the game. Okay. So we are using GCC with -03, which is normally reasonable. We should expect relatively optimal performances. After that, we will try to run it with one task. So it's a serial sequential job. The first parameter is the size or the order of the matrix, and the second one is the number of repetitions to make some longer execution. And we will see here the cycles for each elementary operation in the dot product, which is a multiply and a add. That can be implemented in some machines as what is called a FMA, fuse multiply add. That will explain this term. So it's one iteration inside the dot product, which is the innermost loop. So it's 3.66 cycles. We will try to do better using CQA. So now we will use MAQAO. Use the report 1. And we will provide the command, which is here aprun-n1. We provide the path to the binary. The command to use to run. Binary will be substituted with the value of this variable. Okay, so maybe I have already some already existing. Okay. So we can use a command line version or a configuration file. So it is described in the slide 20. So I have prepared for you a configuration file, which is ov_wig.lua that can reuse elements that are entered in command lines. So it is as you prefer. You can use the one-liner version or the configuration file. In general, as soon as you start to have MPI command, run command, etc., that begins it starts to be interesting to have a configuration file. So here it's finished. So to view results according to if you are on Linux or Windows or on Mac, you can use the most convenient way for you. That can be to create a tarball and to SCP to your local computer, or if you have some even on Linux, maybe Windows, it could be possible. You can mount the Archer directory with SSH-FS, like I will do. So it's you can see a change of background. So it's a black background. That means I am on my local computer. So I just need to create a directory, an empty directory. I mount with SSH-FS. And I now have access to my files. So for instance, here I will directly open with. So I can even go to the directory and open Firefox. So that is in MAQAO Endzone, matmul, ov_orig, like original, results. I am using the tab key to auto-complete. And that's it. So for me, that will open a window so that I can try to share if that works. Normally, you should see a Firefox window with the results for this run. We can see here the total execution time, some vectorization speedup potential, which is 8x. That means clearly we are very far from a top performance. So clearly this is not vectorized. And after that, we can see the tabs already presented by Salah. And we can double click on the, here it's functions, here it's loops. We have the hottest loops here, and we can view the source code. Here we can see the dot product and have confirmation of that the loop is not vectorized. Don't hesitate to use help. So you have some question marks and you have some inline help. You can also use MAQAO.org. In the website, you can have access to some documentation. The quick reference sheet is already on the workshop website, but you have also here. You have some quick guide for LProf for one view and for CQA. CQA and LProf being that can be used standalone. So in some cases that can be useful to bypass one view and directly use LProf. But 90% of time you should use one view. It's the best way to benefit from MAQAO. Okay, so MAQAO.org. Normally the website is you have the URL. Okay, so I will go back to the presentation. Okay, perfect. Some people need some more time to open results, to view results. So with SCP or SSH or etc. So I will continue. So you can also use the text format to visualize results. So I will go back to my console. With just a similar command. So now I no more need to run, so no more need to MPI command, no more need to binary, no more need of run command. Just MAQAO when view create report equals 1, xp equals ov underscore orig, output format equals text dash dash text dash global. And we can see an equivalent of the HTML page directly on your cluster, on the Archer cluster in text version. So it can be quite convenient. So we can retrieve here the execution time. We can retrieve here the bad vectorization status, since we can have 8x speed up by vectorization. And we can see top 5 loops here, which is slide 23. And we can see here the loop 2 should be interesting. It is in the top 5 loops. So hot loops, we need to dig into the second loop. So we will use the CQA analysis for this loop with ID equals 2. And now we have equivalent of the HTML version, but in text format. You can see in particular that the loop is not vectorized. I let some time if you want to see by yourself. Okay, so next slide. So we can see here the issue about vectorization. We are clearly here using only one element in vectors that can support 8 elements. Consequently, and we have another issue. We have some chat messages, but I cannot have access to the chat while I am presenting, so it's not convenient.
We can see the report actually right now, so maybe it will be interesting to show the report or the slides.
Okay, so I switch to the slide. No, but normally everyone can see the slide 25. So on this slide, we can see the 2 elements. So vectorization is not applied, and in case of 2D arrays, so that is the case, we should permute loops. So that is the MAQAO report. So I will try to switch to slides. Okay. So a problem with the present implementation is that elements are not accessed in the same order as they are present in memory. That means there is a gap between each iteration, each element accessed in the dot product. Elements are not contiguous at all in memory, and you have a gap of, for instance, 100 elements if the matrix size is 100 per 100. So it's very bad in memory. So the change that will be applied here consists in switching, in permuting the 2 last levels loops. So instead of ikj, we will switch to ijk. So I will go back to the end zone. No, that doesn't work. I will try another stuff. I will try this. Ah, it's better. Okay. So now we will compile the next implementation. Instead of matmul orig, we will use matmul perm, like permutation of loops. Instead of 3.66, we have much better performance, which cost has reduced to 0.78 cycles per dot product iteration. We will rerun MAQAO and just replace orig with perm. Okay. We can see results in the similar way. I will not go back again to Firefox. You can see on this slide 29 that now execution time is 4.57 instead of 22 seconds, so it's much better. Vectorization possibility to gain performance of speed up by vectorization instead of 8x it is now 1.7. So we are much closer to the top performance by vectorization. And MAQAO complains about compiler flags. It complains about missing march equals target and missing f unroll dash loops. So it's about loop unrolling. And march equals, it is about architecture specialization. So in next slide, we will open again the text output for the hottest loops. Now it's no more 2, but it's 5. And we can read your loop is vectorized, but using only the half of vector length. And we have some help. He killed, process killed. Okay, what happened? No, not, no, oh, okay, killed again. So I will reopen a new one. The reservation is full. Okay. Okay, so I resume the. Okay. Okay. So we will try with march equals core avx I, like Ivy Bridge, since Archer compute nodes are Ivy Bridge. That will improve in 2 ways. Ivy Bridge is not enough recent to have FMA instructions, but it still allows to have 256 bits vectors instead of 128, and that explains the message that you have read on the CQA report about only 128 bits used out of 256. So on the next slide 31, you can see some figures that explain why we can have a 2x speed up by telling your compiler that on the target processor, vector length is 256 bits and not 128. We will now take into account what CQA advised. What is this? Switch. Okay. I need to go back to GNU. Okay. I can see the result. Yes, I need parameters. instead of 0.78, it's now 0.56. So we still have got some speed up. So I will run with MAQAO. So when view, create report with level 1, MPI command is still ap1-n1 for one wank, sequential job. Binary, I provide the pass, the executable, when command, and an experiment pass. I do some cleanup. I don't know if it's required, but I prefer. And that's it. That runs. Okay, and now we can see still speed up. It's now 3.20 seconds instead of 4.57, so it's better. The MAQAO tool is no more complaining about compiler flags, and vectorization speed up is now close to 1, so we have no more possibility to optimize. In other words, we are close to top performance for vectorization point of view. So to sum up, I will switch to this slide. Oh, I don't understand. Slides are presented. Ah, yes. I was showing my screen, so that has changed. Okay. So now we can see the overview of what we have done. We are gain 6.50 x speed up just by following MAQAO hints, and it's quite easy. And you can see that even if O3 compiler option, you still have some room for optimization. We can continue with the Hydro benchmark. So it's a stencil code with it's a 2D stencil with distance 1, and we will try to optimize this. So it is much more difficult compared to matrix multiply. So probably we will have less gain, but still MAQAO will be able to help you with that. So I will exit my interactive session, okay, and I will start with slide 36. So I will share my my screen. Okay. So I have exited my session to have a. I will create a new one. Okay. Perfect. So we will reopen a new session. 20 minutes. I think I prefer to have 30. Normally 20 is enough, but okay. I will reload environment. And this time we will use Intel compiler instead of GNU compiler. Okay. So we will go now to the directory with the hydro hands-on, compile it. I will do some cleanup. Sure. Okay. I am now on slide 38. Okay, so we have a first reference performance, which is 2000 cycles per element, per matrix, per mesh element. We'll try to improve this with MAQAO. So for this MAQAO one view, MAQAO, okay, it's a good one. So MAQAO one view, create report equals 1, xp equals ovk0, config equals ovk0.lua. You can use, if you prefer, -- config, but I think it's more convenient to use C equals. File after some time, okay. After that, we can look at the output. Text output, but I will try to share with the web version, so I will use my SSH mount point. So it's no more in matmul, it's now in hydro. Okay. We can see a report, so with more loops than just 1 or 2 for the matmul benchmark. Most of time is spent in 3 functions: velocity solver, density solver, and project. And about loops, we can see the same loop, the same source loop, but duplicated in assembly code as multiple multi-versioning. So multiple versions of this loop was generated. That means if you are optimizing one, you will optimize the other. So just take the first one. We can see here the computation kernel with a divide and the stencil. We have various indications there, especially about vectorization, but that will be difficult to vectorize. Still, it is a stencil, so we have dependencies from everywhere. We can see that we have some inefficient array accesses. Here, that will be difficult. That is not applicable here. We have no aware of structures, so we will continue to read. We can see there is no one wall, Still, we retrieve from the source code 4 additions and 1 multiply. The divide has disappeared. So I think here that will be automatically substituted by the compiler. But we have a hint here about loop unrolling. Here, MAQAO detected that the loop is possibly data access bound, so limited performance is limited by reading and writing the data to arrays. And MAQAO estimates here that unrolling could help. For instance, via a compiler directive or manually. So we will do this. So I go back. Presentation. And slide 41, that we will explain what is happening. So it's more convenient using slides. So 41. Okay, it's loading, it's loading, it's loading. Okay. So you can see here the stencil on the first position on the grid. If I scan the iteration space, we can see at some point that we have reuse. Some elements was already loaded from memory. The compiler can exploit this. It cannot exploit this automatically in that case, but if we force unrolling, we can expose this situation to the compiler, and it will reuse the loaded elements. So instead of reading again the memory, it will reuse the already fetch value. I continue, and we have some nice effect. If we continue to scan, here it's to unroll in both directions, I and j. So if we count, we can see 1 plus 2 plus 2, etc., etc. We can have a total of 32 elements saved from being read again from memory. That means we can use memory 48 times instead of 80. So we can divide by, not by 2, but close by 2, the number of the pressure on memory load. That should be efficient if the kernel is actually memory bound. So we can rewrite the source code by using a macro here to express the invocation of the stencil in one point, and we will unroll by 4 in both directions, like presented in the figure. That means 4 multiplied by 4 is 16. So we'll have 16 stencil points per iteration instead of 1. So I go back to 2 slides. So 52. So we will execute the next version, which is the version 1 instead of version 0. Instead of 2000 cycles per element, we have now 900. So it's more than 2x better. We run one view. With a configuration file. Okay, and display results. And we can see here the improvement in total time. And that the hottest loop is now the 147th. So we will open for this loop. That can be done with the HTML interface, as you prefer. For me, for hands-on, it's more convenient with text. So your loop is still not vectorized. But now we can see instead of 1 or 4 multiply and 16, we can see here the effect of an unrolling. So we have 16 more operations per iteration. Okay, so we can see now we are loading 68 single precision elements. We would have preferred 48, but it's still better than 80. So we have some gain, already some gain about the pressure to read memory that explains the speed up. We go back to presentation. So hands-on is finished now. So just to see the summary slide, the last slide. To sum up, we have now 2.5x speed up just by following the CQA advice about loop unrolling. And so here we have applied this manually, but with Intel compiler, you could use a directive, which is unroll and jam. Unroll and jam for non-enormous loops, and unroll for enormous loops. And in between parentheses, the unroll factor. So it's another possibility. So that's finished for the second CQA-oriented tutorial. But now we have more codes. For instance, some small loops. But my colleague Salah will present you, I think, more interesting small applications, so mini apps, and you can play with the apps. So he will present this. If someone has already an application running somewhere on Archer or elsewhere, we can also help her or help him with his own application, and not some mini apps. So it's as you prefer. So we are now here to help you to optimize applications with MAQAO. So I leave the speech to Jasper. Have you any questions? If not, so I leave the speech to Jasper.
Hello, can everybody hear me?
Yep.
Good, thanks. So I'm in charge of the second part of the hands-on, so we're gonna have to, let me check here, share. I think these are, so we ran actually this morning, we ran on BT, and I showed you a brief example of a Lulash run. So we're gonna dive a little bit more into Lulash, and then let me just go on here. Yes. So what I'm gonna show you now is the scalability report part of the MAQAO OneView module. So it's a pretty interesting output where we study the scalability of an parallel application, and it's done automatically actually by the tool. So same as this morning, you have to configure your environment and compile the application. But I'm gonna do everything. I'm gonna share my screen and show you actually how to run all of the reports. And one thing we're gonna do after that is play around. I prepared some toy codes that we can look at and that you can just play around with. And I'm gonna give you a list of interesting applications, some proxy applications that you can download later and play on your laptop, or just an example code that you can just apply the tool on, and all the other tools that you saw during this this workshop. It could be very interesting if you don't have your own codes, but if you do have a code, try to apply the tools on it. And if you have any feedback, I mean, we be very happy to see if you have any issues or if you have any remarks or propositions. So let me share my screen here. This is not, yeah, it's over here. Okay. So you should see my terminal. Yep. Is the font size okay? Should I increase it a bit more? It's all right. All right. Maybe increase the font size. Okay. It's good. Everybody can see. Okay. So we're gonna start with looks okay. All right. We're gonna start with Lulash. It's we're gonna kind of pick up where we left off. I'm gonna remove all the MAQAO analysis I did before on a fresh. So everything we need. All right. So as before, I'm here actually. I didn't see I was on an interactive session. I was not actually on the login node. So first thing we're gonna do is open go into the Lulash environment, and I'm gonna run the same command I was gonna run actually before this morning. But what I didn't do is I didn't add the scalability report. So what you saw is just a single process, single thread Lulash running. But now what I'm gonna do is run it with a scalability report. So same as this morning, you have to load the environment. And if you did this and you still have the active session going, it should be still, MAQAO should still be in your environment. So I'm gonna run a OneView. Oh. create report is equal to 1. And then we're going to provide a configuration file, which is the config Lua. And in here, we're going to add with dash scalability. Now, these commands, actually, you can find them in the quick reference guide or quick reference sheet that was provided. You should find these on the first page. All the one view options that are extremely useful. Like in this case, I can just say that scalability mode is on.
You
and
have
then
you have a typo in your comment. It's not about config.
oh yeah, yes, thank you. Figured it out the hard way. So here actually I'm going to run this this profiling, and then the application is going to go just like you saw this morning, but we're going to have an additional thing to the added to the previous results that we saw this morning. So let me switch here into a different. Move these ones. So now the application is running and the profiler is finishing up. So we should have scalability runs going on right now. So you should see that running the profiler for scalability and compare analysis. So it's going to do multiple runs, and we're going to get very interesting output out of this. Now this is running on Lulesh. It's a application you can just download from the internet. It's available. I guess it's Lawrence Livermore National Lab code, and there are many other proto applications that if you don't have applications yourself, or you still developing applications and you would like to play around with these performance analysis tools, you could pick one of them. I'll provide a list actually at some point. Maybe play around with a couple of these applications. But some of them require a lot of libraries and maybe some environments like Cocos and other Charm++ and other environments that are not necessarily available everywhere. But you can play with these actually on your laptop, so you can familiarize yourself with the performance analysis tools and all the outputs and metrics and all this. So what we're also going to do is try to compare both compilers available on this machine, so we can see actually which one is more suited. So I have a bunch of toy codes that we're going to look at and try to see how MAQAO can help. You can do a little bit of code optimization by hand, or at least just changing the code patterns so that they can fit into something that the compiler can easily optimize, and then check whether that happened or not using static analysis and doing some performance analysis to see whether the time spent doing optimization actually was fruitful or not. So now one view is running run number 4, scalability mode. So what this mode does is just runs the application with an increasing number of threads. So if you have a parallel program, like in our case, Lulesh is a parallel application, you'd like to see how it evolves depending on the number of threads you use. Is the parallel model implemented properly? Is the number of threads at some point going to bring some issues that were not really seen before because we didn't necessarily test on the big machine? And this is the kind of problem that you usually have when you deploy a supercomputer. You develop code and you work on a certain machine, and let's just say that it has 10,000 compute nodes, but then when the 100,000 compute nodes machine shows up, your performance is totally nonsense. So this analysis allows to study actually the evolution of the performance and the behavior of the application with an increasing number of threads. And more and more actually parallel compute provided to the application. So here we have this directory. So I'm going to see how large it is. It is around 200 meg. So let me hard this thing, and then I'm going to download it so we can open it up on my local machine. I just changed the name. Lulash run 0, for example. Okay, I'm gonna compress this from 0. Once it's compressed, lulash underscore run something here. Now, usually if you're working on an application, you do multiple profiles, you do multiple runs, and then you just pump most of the data. Or if you have an SSHFS, it would be easier actually, but I didn't in my case because I'm not using SSHFS. So this is done, and I'm gonna move this one into my directly and download it back in here. See. So soon we'll be able to look at the data. Okay, that's good. Right. So here we have our experiment directory. So we're going to go into results, index.html, and we're supposed to be here. Here we go. So here we have the analysis of the binary file running, but apparently it didn't run. Oh, I made a mistake. I must have off. Shoot.
No, it did work. It's just that I don't think it appears in the recap, Sana.
It doesn't appear.
You can check. Yeah, if you no, I don't think, because you can see where we have the scalability, ideal speed up in the global metrics. So I think it works.
Yeah,
check in the application tab, but normally it's okay. Yeah. You have the various scalability views.
Yeah, they're here. Yeah. Okay, so I thought it was showing up actually on front, but it's okay. So here actually we can have the scalability runs, and we can have the scalability data. So you can clearly see around here that we have a reference run. It's the first bar you can look at. So this is like the baseline with which we're gonna compare all the different runs. And for each run, you have here actually a legend that shows you where time was spent. So whether it's an NPI, OpenMP, or a system, or something else, if there is anything else that shows up. So this is the scalability coverage per category. If we go into the scalability efficiency, you can clearly see here how the program evolves from one run to the other. So clearly this, so higher is better. If you look at the bars or histograms you have in here, clearly the run number 4 is definitely not efficient compared to the reference run. We can switch to the based profile, and this is a view where we can see the number of functions on the left axis, and on the right axis you have the coverage. And then here you have the different statistics for each and every function. So you have here the number of functions that are higher than 8% and between 4 and 8% and so on. Now look at the parallel efficiency. We can have some more details in here. We can see that for the first run where we ran with 6 threads. The second run where we run with 8 threads, and another 8 threads run, and a fourth run when we ran with 48 threads. So obviously in here we can have a much general view, and then here we can see the speed ups, and the same thing, we can have a much better view with the detailed coverage per parallel speed up. And we also have actually pop metrics added to one view because MAQAO is part of the pop project. So there is a specific definition, and we comply with the definition and the standard, given that we have a close relationship with the pop project. So in here, same thing as before, we still have the configuration. Here we're going to have in the topology a little bit more why are there 2 runs with 8 threads? Okay, let me go back here.
Normally that's because they should have 2 different configuration. If you hover over the name or over the name of a column, for instance, you should have a description of the run. If you over run 1 and 2 in the x-axis of the graph, oh yeah, here is as well, and
Yeah.
show one of them should have 8 process, 1 thread, or something like that. If you
this one has 1 thread and runs on 1 node, and it has 8 processes. And this one is the same. But if you see the difference is the number of nodes and the number of tasks per node. So this one runs on 2 nodes with 4 tasks per node. And the second one, or the second one, runs on 1 node with 8 tasks per node. So it's pretty confusing if you look at just this column, but you have to go look at the detail of the run. So you have 4 tasks spread across 2 nodes, or 8 tasks assigned to 1 single node. But it's still 8. If you look at the number, the number of observed threads in total, it's going to be 8. Just that the topology is different, and this is what I was looking at in here. If you go into the topology view, you have a much clearer view for each thread. So here clearly you can see their spread node by node. Okay, so for the first run, you can clearly see that you have 1 process with 6 threads total, and in here we have 1 process with 8 threads total, and here we have 2 processes on 2 different nodes with 4 threads each. So it's a total of 8 threads. So I don't know. This should actually answer your question in a very detailed way, and you can also see the time spent and the coverage for each and every thread you have running. So here for the 4th run, we have 2 nodes with a total of 48, 24 per node, 24 threads per node, and a total of 48 threads for the whole run. So of course, for each entry you have here, you can click and obtain a profile for each thread and start going around. Like for example, here we can see that loop number 81 covers around 11.31% of execution time. You can go and, just like we did this morning, look at the CQA profile, look at the assembly code, if there are any call chains available. Here we can see the call chains because they're available, so we can click in here and see where does the function come from. And at some point, of course, we'll lose track of program execution. We can see the load distribution here. Also for all threads, and this should be the source code back in here. So all of these views all of these views actually are available with 1 view, and all we have to do is actually run 1 view. So in this case, we run it using a batch script. So you check for thread spinning to cores. I don't think there is a thread migration watchdog or something like that. Thread pinning, yeah, but it can be configured. Yes, you can tell MAQAO or OneView in this case to do a run with a certain configuration, but does MAQAO verify whether a parallel application is doing thread migration? No, but OneView can launch a specific configuration. I mean, this is exactly what we were looking at here. Let me open this one up back. It's exactly what we were looking at in here. It's this scalability run is capable of going through different topologies. So as you can see in here, we did a run on a single node and did 2 runs on a single node and 1 run on 2 nodes with different number of threads. So this is controllable. I mean, you can control the way your application is launched. Just a matter of changing the configuration file to suit your run requirements. But for detection, no, it's not. MAQAO does not detect whether a thread has been moved from one core to the other. So this was an example on Lulash. You can try to reproduce this one. You can try to play around with this application because you can clearly see that there is still some work to be done on Lulash. It's not really an optimized application. So this is a simple first example where we can see the scalability run. And we can look at another. I mean, we can look a little bit more at Lulash if you want. Look at some additional loops like why. I mean, what is this loop doing? It's taken up 15% of total coverage. We clearly see here the distribution. I mean, we use a color code to show the hot loops from the cold loops. We can also here try to play around with let's just say vectorization ratio. We can add a column in here and see actually, so this one has a 13.52 vectorization ratio. And it's pretty easy. We can check this, we can look at the assembly code if we want and see here that CQA is supposed to report something similar. It says that only 28% of vector length is used. This is what we saw this morning. So there is some room for improvement in here. So we can go around and poke around in the make file. If we want to optimize Lulash, we can start doing some optimizations. There are many things we can add in here. We can see it's already using an O3 optimization flag. It's already using an OpenMP flag. But there are many flags we can add, but you have to look eventually at the source code and see whether the source code fits what the compiler is expecting as patterns. But eventually here we can clearly see that this source code with the compiler flags that we provided does not necessarily give us the best assembly code we can expect. So this is partially vectorized, and the compiler can do much better. So, and this has been compiled with GCC. So if we look in here, we should be able to find actually information about. So these are the compiler flags that were used. So core i7 AVX, but we didn't see any AVX code generated, though it was specified to the compiler. And we clearly see that we're running on a GNU 6.3 Cray version of GCC. We can go look at the functions if you want. But as I said before, it's mostly going to be loops inside functions. So unless the function has been inlined within the loop, usually there are rarely functions. Actually, there are hotspots. So we can add actually many other columns if we want. We can see even here speed up if no scalar integer. So how much would we gain out of removing all scalar integer? I mean, we wouldn't gain much, but we would gain 40% if we vectorized all floating point instructions. So this is or here for the second loop, we can gain 80% if we vectorized every instruction in the in the assembly code, or if we make sure that the compiler generates vectorized code. So these are speed up projections that could help evaluate whether I should vectorize or not. Should I spend time trying to vectorize this loop, or trying to find the compiler, or lure the compiler into doing what I want it to do? And usually these are helpful for programmers who develop tools like Lulash. And also, if you are an HPC engineer and you happen to get an application that you have to work on at some point, and you have to optimize it, even though it's not necessarily your area of expertise. I mean, tools like MAQAO and OneView can help you very easily at least get a hold of the situation and understand the basic metrics and the basic environment in which your application is running. And then in here we can add actually so many other columns specific to each run, and you can select everything and look at the whole matrix. But this starts to get a bit cumbersome at some point, so usually stay on coverage, maybe timing and vectorization ratio would be very interesting for people who are doing code optimization. This is a good beginning actually to start digging deeper into what's happening. So for Lulash, for example, we can spend some time looking at the source code and try to go and see this specific function, which does nothing but load a two-dimensional array and perform some computation. Oddly enough, here we can see some multiply and accumulates. So I didn't see any FMA instructions generated. So yeah, so you can clearly see here the limitations of compiler-generated code when the compiler is not driven properly. So this is the first example, and we can look at something more interactive. So I think I copied a couple of a tar archive. Feel free if you have any questions. You know, don't hesitate to interrupt me. I could bounce back on anything, anytime. So I prepared a bunch of toy codes. I don't know if they are. I couldn't copy it because I didn't have the permissions. So I tried to copy. I try to copy actually the tar file here, but Emmanuel didn't give permissions to the groups, so I cannot really copy this in the MAQAO directory. Because I guess it's Emmanuel who created the directory. So it was work TA002 and shared, and yeah, same problem. So these are example codes if you want to play around with them. So I can clearly see here that we don't have group. We do not have group permissions. Yeah, well, let me show you that again. So you can clearly see here actually in the first page of the report that you have here a potential speed up for each and every case in here. Okay, if the whole loop space was vectorized, you will gain like 96% speed up. So almost you double the performance of the application. So technically you should move from 24 seconds to something like 12, 11 seconds. So this is what it means. If you optimize everything and vectorize everything, it should technically run twice faster. If you optimize only floating point instructions, you should reach something like 24% performance increase. And if you do no scalar integer, what you get is like 3% improvement. So what you can see in here is actually the potential speed up for the whole application. And now if you want more details, you can look in here to see actually the potential speed up for each and every loop and the evolution actually, yeah, I was gonna switch to the loop tabs, so you can clearly see here where is the speed up. Loop speed up. Where is the perfect load balancing? I think we should be set here. So what you have in here is the different potential speed ups you get for each and every loop that was measured.
Yes, but if I understand it correctly, that speed up, for example, 3.5 is the speed up of a given loop. The speed up for the code will be 3.5 times this 14%.
Yeah, well, this is here.
So
this is the part where you see that.
Let's see in the loop, on which loop I should concentrate, because that gives me the best benefit for the whole code.
Oh yeah, so you can have that in the graph on the first page. If you click on one of the categories, Jasper, on the for instance, fully vectorized, you can see the graphs. You can see for each loops.
Oh, you mean? Oh, okay, okay, yeah.
Oh, okay,
Yeah.
that's good.
Yeah.
And you have here the cumulative speed up. So you can see the first loop to focus on, and then the
it was the cumulated speed up. I didn't understand actually that it was the cumulated speed up. I'm sorry.
Yeah, it is exactly what I said.
Thanks. Yeah, well, this is what it's right over here. You just double click actually on the fully vectorized, and you get different graphs actually for each one of those projections. So like for the whole application, this is what you get. So it's the cumulated speed up, yeah.
And if you click on a dot in the graph, you can directly open the report on the corresponding loop.
Yep. So for example here, I clicked on loop number 107. Obviously same analysis, so we can get a 2.13x speed up on this loop, specifically moving from 20 cycles to 9.38 cycles. This is based on a pipeline, static pipeline simulation. So clearly here, code is definitely not vectorized, and it just needs more vectorization. So this code, oh, sorry, I dropped my phone. So here, what you should find is the cumulated speed up, and then you can click, as I did here, for example, and see that we have loop 108 as the loop of interest in here, and it is 29% efficiency. So it is not using full vector length also. So this, if we look at the assembly code again, we can see some scalar instructions, and yeah, a little bit of vector instructions in here, but the compiler could do better. And we can clearly also go into the scalability run, and here have the scalability speed up. So clear see here, it's the higher is better. Therefore here we can clearly see that compared to the reference run, the most efficient one is the run number 4, where we run with full threads on a couple of nodes. So obviously this code evolves well, but we should maybe push it a little bit more. But depending on the architecture you're running on and the number of cores and nodes available, you can do multiple runs. You can add more nodes, you can add more threads. As I said, depending on the architecture you're running on, you can just go and explore actually different topologies. So I guess Emmanuel fixed the copy issue, the group issue. Let me copy this. Yes. So you can get these codes here in the /work TA 002 shared MAQAO. Just codes.tar, and if you untar it, you should find two codes that perform a Hamming distance that are pretty interesting because it's a case where a data type is an obstacle to vectorization, and that's pretty interesting to look at because all you have to do in this case is refactor the whole code and rewrite it with a more suitable code pattern. And I've provided a lot of variants actually that you can look at. You can just go straight away. Now, this one is a simple kernel that performs a Hamming distance. So it's going to load a file with a sequence, DNA sequence or an RNA sequence. And what it's going to do is perform a XOR operation between both arrays and calculate the number of ones and zeros in each and every result of that XOR. So it's a pop count. Now, this is one way of calculating a Hamming distance is taking both binary representations of the symbols we use and then applying an XOR operation, as you can see in here. So we take the first sequence P1 and the second sequence P2. Now this is a pointer towards the sequence. And then we XOR both bytes. And then when we XOR these bytes, we apply a pop count. So we're going to count the number of zeros and ones in the binary representation of that result. And that number is an integer that we're going to accumulate. And the number of bits that are different from one sequence to the other is the distance between these two sequences. So this is sometimes used in genetics. It's a tiny little kernel, but it's sometimes used in genetics to compute the phylogenetic distance, and sometimes also used for verifying floating point calculations, the accuracy of floating point calculations, especially sometimes in highly accurate cosmology codes. They do have gigantic files that eat up actually kind of like a lot of space, and it's gigabytes of files with floating point data that you have to check and verify for a certain precision. So this is one of the loops that you can find sometimes in these codes. And I chose it because it's pretty interesting because the Intel x86 architecture provides an instruction that calculates pop. A lot of compilers provide intrinsics for a pop count, but depending on how you compile your code and how you provide parameters to the function, you're going to have different results. And the thing is, in here, the obstacle is a data type. So the data type that's used is algorithmically viable, but in terms of implementation, it hinders actually a lot of optimizations because not only we use in C with pointers, so we're making things hard for the compiler, but also the fact that we use in characters does not leave any room for vectorization for most compilers. They don't really give that much importance to vectorize an integer code and pop count and things like this, though this kernel actually shows up a lot in a lot of genomic and genetic codes. So this one is pretty easy to compile. We just have, I'm going to have to load the Intel compiler. So it's going to be version 17.0.3, if I'm not mistaken. 0.191. So you have to load the Intel compiler. So go with the module load Intel 17.0.3.191. And should be able to compile two versions, a dist.g and a dist.i. So G is for GCC and I for ICC. Now, if you look at the make file, there are no optimization flags, so it's up to you to see, actually play around and see how this code evolves from one optimization flag to the other, from one maybe code change to another, and see what MAQAO gives you in return. You can use MAQAO actually, as Emmanuel said, you can do cross analysis. Like you could be working on this binary file that is meant to run on a Skylake or maybe an AMD machine, compiled with another compiler than the one you're working on, but you can still do CQA analysis. For example, I can do MAQAO analyze -ll to list loops, and I can just pass it my binary file, And what it's going to do is going to go through the whole program and find the functions and the loops. And I have a function here called distBaseline, which is the C function that I just showed you that does the XOR and the distance using the pop count. Okay, so I have to change my permissions to. I guess there's an issue with the file that tar file that I copied. Okay, let me fix this quick. Work PA002 shared MAQAO. Yeah, well, I didn't copy with group permissions. chmod. Maybe others. No, it should be okay. Should be able to copy it. Yep, good. Now, go back to what I was saying. Yeah, we can run actually a MAQAO analyze binary file, and we can just go and locate this function. So it has a loop, one single loop, exactly as it is shown in the source code. Now, because we're not using any compiler optimizations, obviously the code is gonna kind of look like exactly as what I've written. So this is going to be one single loop, one single function, because there's no optimization. So the compiler does not do much but generates just this stupidest, simplest code that works. Now, if we start adding more optimizations, we're going to see the binary start to change. But what we can do here first is run, for example, a CQA analysis and run it on loop number 1, CQA, and we're going to ask for loop number 1, and the binary file is going to be dist.v. Now you can have these commands; they're already available in the quick reference sheet, but you can also run them at the same time, and you can get a report. Now, what does CQA say? The loop now it finds the line numbers of the loops on the file, which is pretty good. We know what loop exactly the tool is talking about. And here it says that only 46% of vector register length is used. Okay, so we should vectorize the loop, and we can gain a 3x speedup by moving from 6 cycles to 1.89 cycles. So the compiler did some work on this loop, but apparently it's not enough, given that we are only 46%. We're not even at 50%. So obviously it might have generated some SSC code, or and I'm doing this actually on the login session. So what I'm going to do now is switch to a interactive session, and go on an interactive session and see here. I'm going to wait for this one to. Yeah. So here the thing is you have to load everything back again. So the create PA2 and PA2. So if you go into the examples directory and toy codes, there's another code that does exactly the same. Now, if you want to use this one, just so that you have a README that explains exactly what you should do. Now, there's a program that you have to compile first that generates random sequences. And I would recommend using actually the commands that are provided in the README to generate 2 sequences. And if you want to play around, you just run one of those binaries, the GNU or the Intel one, on both sequences. And the tool is supposed to compare and return actually return the distance between the 2 sequences. Now, there's another code that does exactly the same, but I've written it in a different way. There are many other options in there. So I have a version of pop count in assembly code and another version that's written in a divide and conquer bitwise manner. So you have multiple versions, you have OpenMP versions, so you can compare actually all these using MAQAO. You can play around and test them. You have an LU decomposition if you're interested in looking at how you can play around with this code and optimize it too. So I put these in there, and in the solutions directory you have a bunch of my own explorations, some of my measurements also. You can find some raw data in here that you can plot. I mean, everything is available in the README files. You can just go in and check them out. You're supposed to find everything to play around and apply the same analyses as I did. Just a simple one view or a CQA and just read the report. And you can apply one view straight away also, like in a command line instead of in a interactive session using the command line. So instead of providing a config file with a configuration for a PBS file, if you run it on a cluster, you can just go in and run everything command line. You should have the commands actually on the tutorial spreadsheet, quick reference guide tutorial spreadsheet. There is another application that could be really interesting if you're looking for apps to play around, and if you don't really have your own code. There's this code called Latte that you can get from a GitHub. Let me get and here you can go in and grab this one up. It's a pretty interesting code. It's written in Fortran, so and it's pretty heavy code. Also, there's a lot of functionalities happening in here, and it's just easy to compile, and you can play around with it if you want to have an idea about how to profile and optimize a Fortran code using MAQAO, and to see that there isn't much difference between C, C++ or Fortran for MAQAO. There's also another mini app that you can try called Mini QMC. I have a list. I'm going to provide it maybe to Cedric, and he will share it with you if you are looking for toy applications, mini applications, proxy apps. We can maybe give you a list that you can play around with. But if you want to also play with some other applications, Emmanuel here has provided some small loops that you can just try to apply MAQAO on and get a hold on loop analysis, loop optimization using MAQAO. If you have any questions, feel free to ask anytime. We're available, whether it is by email or right now. If you have anything to ask for, if you have any feedback, feel free to express yourself on the chat. Thank you.
Thank you, Sarah and Emmanuel. So I guess we'll now pause for the lunch break, and we'll resume at 2 p.m. BST for the Forge presentations.